Yeah, good morning my dear students. Today I am going to discuss the topic on FTIR spectrometer. What is this FTIR? FTIR refers to Fourier transformation infrared spectrometer. How this is basically working? Basically you should know that what is the meaning of a Fourier analysis. The Fourier analysis is a procedure in which a curve is decomposed into a sum of sine and cosine terms called as Fourier series. I repeat it. A Fourier analysis is a procedure in which a simple curve is decomposed into a sum of sine and cosine terms called Fourier series. So what is this term? Basically, if you look at this Fourier analysis, a curve is having basically two components, right? One is the sine component, another one is the cos component, right? For example, if I take on the x-axis 0 to 10 as an interval and y-axis I am taking from 0.1 to 0.5 as an interval. Now to analyze the curve with the spans the intervals from x1 is equal to 0 to x2 is equal to 10. The first x1 is equal to 0 and x2 is equal to 10. The Fourier series has the form. The formula for Fourier series is y is equal to a0 into sine of 0 omega x plus b0 into cos of 0 omega x plus a1 into sine of 1 omega x plus b1 into cos of 1 omega x plus of etc. 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 Right? So y is equal to summation of n is equal to 0 to the power infinity an into sine of 0 omega x. Instead of 0 omega x we are using n omega x plus bn into cos of n omega x. So this is the generalized equation for Fourier analysis, where omega is equal to 2 pi divided by x2 minus x1. So x2 is the maximum interval and x1 is the minimum interval. So that is 2 pi divided by 10 minus 0 is equal to 2 pi divided by 10, which is equal to pi by 5. So omega is the amplitude or double the frequency, right? Now why we are using this Fourier analysis? Basically when I use this Fourier analysis, we are using some coefficient, that is we are using an, bn, these are the two terms we are using. These an and bn, these are the Fourier coefficient values. When I talk about the Fourier coefficient values, they have the fixed values, they are the constants. So when the number of interval is 0, an is equal to 0 and bn is equal to 0.137. If the number of interval is 1, an is equal to minus 0.007 and bn is equal to minus 0.161. Right? So like this, these values have been already reported in the table of literature. Now what we are doing, based upon these values, you have to apply the Fourier series reconstruction curve. Suppose if your curve is having in this manner, suppose this is a curve I am having, there are three graphs I am showing here. In the same graph I am showing three curves, right? So x versus y we are showing. In the first curve, this is the original curve, and the Fourier reconstruction curve, if I am making with the coefficient values, then I am getting this type of curve, which is not matching perfectly. So why? Because n is equal to 0 to 2. I am taking only three Fourier coefficient values. N is equal to 0, n is equal to 1, n is equal to 2. If I take these three values, the curve is not fitting exactly with the original curve. That is the reconstruction curve is the dotted lines and the original curve is your expected curve is this one, right? Now what I am doing, in the second one, if I apply the intervals from n is equal to 0 to 4, in that case it is somewhat matching but not accurately matching. Whereas if I go n is equal to 0 to 8 interval, in this case what will happen? The curve will be perfectly matching. That means you cannot differentiate the original curve as well as the Fourier reconstruction curve. Because Fourier analysis is a mathematical procedure. That is a very important aspect. So when you apply any mathematical procedure, it should behave in a proper manner and that should coincide with your sine and cos terms in the simple curve equation. Right? So this is the meaning of this, right? So the coefficients are required to construct the curve. So you need the coefficient to construct the curve also, and the larger the coefficient values, the more the term contributes to the sum. So here I am having larger coefficient values, for example 0.137, right, 0.008. When you have the larger coefficient values, they contribute more to the sum. Why? Because sine square theta plus cos square theta is equal to 1. That is the reason the larger the coefficient values, it contributes more to the sum term values, right? So this is all about the Fourier analysis, right? How far this Fourier analysis has been used in your FTIR spectrometer? That is what we are going to discuss in the next slide, right? So what is this FTIR? FTIR means the Fourier Transformation Infrared Spectrometer. So you have to transform this Fourier analysis as a mathematical procedure, as a software. We have to install this Fourier analysis and then we have to use it for your FTIR spectrometer, right? So that is the next important aspect, right? Is it clear? Now, when I talk about this FTIR spectrometer, here we are not using any monochromator. Only in dispersive IR spectrometer we are using monochromator. Here we are using Michelson interferometer. Okay. So this interferometer is having this type of arrangement. So here we have the light source, IR light source, preferably the globar source. And here we are keeping one stationary mirror and here we are keeping one movable mirror. We have one stationary mirror, we have one movable mirror, and in between these two things we are keeping a beam splitter, right? So the beam splitter is basically made up of germanium layer evaporated to potassium bromide plate, which can be used for regions from 4000 to 400 centimeter inverse, especially for the mid IR region. And sometimes if you want to perform this interferometer for far IR region, we are using mylar as the beam splitter, which is covering the range of lesser than 400 centimeter inverse. Now, when I pass the light radiation here, so this is a monochromatic source of light radiation from the globar source. When I pass the light radiation here, so what they will do, they will hit the beam splitter. Once they hit the beam splitter, some of the light radiations will get reflected, some of the light radiations will get transmitted, right? So the reflected light radiations will go and hit the stationary mirror, whereas the transmitted light radiations will go and hit the movable mirror, right? So once they hit the stationary mirror, again they will reflected back, and once they hit the movable mirror, again they will be reflected back, right? Now these two incoming radiations will converge in the center point and they will undergo the constructive interference. This is a very important aspect, right? So the light radiations will go towards this terminal, again it is coming back, and here also it is going up and again it is coming back. So the incoming radiation, both the incoming radiation which is coming back from the stationary mirror and the movable mirror, they will coincide or they will undergo the constructive interference, that is they are in phase with each other and they will be going and hitting your sample cell which contains your sample. After sample you will be keeping your detector. Detector is basically the pyroelectric detectors which we commonly use in FTIR. Basically we are using detectors like DTGS, deuterated triglycine sulfate, as a detector, right? Now what is happening here, everything depends upon the movable mirror. So initially the movable mirror is also fixed. The movable mirror is also fixed. We call them as a delta value which is equal to 0. Why we have fixing the movable mirror? Because see what will happen. This is O, this is M, this is S. That is the distance between the beam splitter towards the stationary mirror. This is we are giving as OS, and from the distance from the beam splitter to movable mirror we are giving as OM, right? Now what will happen when the stationary mirror and the movable mirror are fixed here? Now what will happen? This is also traveling the same distance. This is also traveling the same distance. So when they both traveling the same distance, so there is no difference in the path length. Okay. So in that case, delta is equal to 0. That means we have to remember what is delta. Delta is also called retardation. That is the difference in path length of the light waves traveled in the interferometer. Okay, the difference in path length. This is the length traveled by the light rays. The difference in path length between the two waves in the interferometer is defined as retardation, which is given by delta. So delta is equal to 2 into OM minus OS, right? Why 2 into OM minus OS? Because it is traveling here and coming back. It is again traveling here and coming back, right? So that is the reason we are using the delta as a retardation factor, and this delta will be 0 when you are not moving a mirror and you are fixing the mirror also, stationary mirror and movable mirror, you are fixing it a particular distance. In that case you will be having the equal path length. Right? We call that there is no difference in the path length. We also call it as ZPD. ZPD refers to zero path length difference. There is no difference in path length between the transmitted radiation and the reflected radiations coming from the movable mirror and the stationary mirror. Right? Now what I can do, I just move the mirror little bit here. Right? So in that case the delta value will be half integer. So here it is 0. Right? After that what will happen? You will be getting half, that is lambda by 2. right? It is a half integer. So when it is going as, when you move the mirror as in a half integer, so in that time what will happen, whatever the radiations coming from the movable mirror and the stationary mirror, they will not coincide with each other, they will be out of phase with each other. So the light waves out of phase and they will try to distract with each other. They will undergo the destructive interference and they will try to cancel out each other, right? So therefore, at a half wavelength, what will happen? Delta is equal to half lambda. In that case, what will happen? You will be getting destructive interference. Again, I move the mirror, movable mirror here. I will be getting 1 lambda. So again, I will be getting the constructive interference. Then again, if I move the mirror as 3 by 2 lambda, that is equal to 1.5, again I will be getting the destructive interference. Again when I move the movable mirror to 2 lambda, I will be getting the constructive interference. So you can see that there is a constructive interference followed by destructive interference. Again constructive interference followed by destructive interference. Simply we can say there is a maxima followed by minima, there is a maxima followed by minima. Right? So this is a very important graph. This is this graph, when we are plotting the output light intensity versus retardation, this graph is called as interferogram. This is a very important aspect, right? So interferogram is a very important concept in your FTIR spectrometer. So interferogram is the graph obtained between output light intensity versus retardation, right? Now you are getting my point. So what you can say that during constructive interference, when it will be having, it occurs when you are having the integral multiples of the wavelength. When you will be getting destructive interference, you will be having the half integral multiples of the wavelength of light, right? Well, here it is 1 by 2, 3 by 2, they are in the half integers, right? So when you have the half integers, you will be getting the destructive interference. When you have the full integer, you will be getting the constructive interference. So this is the way you can measure the difference in light waves as such, right? So that is the thing you should remember. This is a very important concept. So if the two waves are in phase, they interfere constructively to give a wave with twice the amplitude. This is a very important aspect. If the waves are out of phase, they interfere destructively and cancel with each other. Or always there is a constructive interference followed by destructive interference, right? So all these things we have discussed here. Now what is this interferogram? I already told you. How will you plot this graph between retardation and output light intensity? And interferogram is a simple cosine wave. Whenever you do the FTIR spectrometer, you always get the interferogram, which is a simple cosine wave, which is a time domain signal. I already told you a curve is made up of both the components, sine component and cos component. But whatever interferogram you are getting, you will be getting only the cos component, right? So you will be getting a cosine wave, right? So you can record the spectra in a very fast manner. This is the concept, right? Whenever, why we are going for interferogram, when you record the interferogram, that is from the source of all wavelengths, right? Contribution from each wavelength can be obtained in case of interferogram, right? So it is a simple cosine wave. It is a time domain signal. Whenever you perform FTIR, so you will get initially time domain signal. Initially you will get interferogram, and this interferogram will be attached with the software containing the Fourier series. You install the mathematical procedure of Fourier analysis in the computer system. So whatever interferogram you are getting, with that your sine function will be attached through the Fourier series, and when we are attaching that one, then finally you will be getting Fourier transformed signal, that is called FT signal. That is basically the frequency domain signal. The frequency, that is wave number in centimeter inverse, the frequency domain signal will be finally coming over there, right? So you should remember that in dispersive IR spectrometer, why it is taking too much time? Because the frequency domain signal, for each and every curve, you have to include both the sine function and the cos function. Therefore, it will obviously take more time when you record the graph in dispersive IR spectrometer, which we are using in olden days. But most of the modern FTIR spectrometers, we can perform the spectra in a very fast manner. Why? Because they are going for Fourier transformation. So initially they will make the cos function only. Instead of making a full curve with both the sine and the cos function, for every wavelength it will take too much time. So what they will do, they will analyze all the wavelength together and make only the cos function as an interferogram. And with that interferogram, if you add the Fourier series or any other mathematical series, automatically what will happen? The sine function will be added, and that will lead to the formation of the full curve as such, right? When you construct a curve, you need both the sine function and the cos function, right? So that is how this is called FT signal, which is also called as frequency domain signal, right? Now, what is an advantage? Why we are using this FTIR? Normally, we can go for dispersive IR spectrometer itself. What is the reason behind using this FTIR? Because there are three important advantages with FTIR spectrometry. The first important advantage is multiplex advantage or Felgate's advantage. What is this multiplex advantage or Felgate's advantage? All wavelengths are measured simultaneously in less than 1 second. This is an advantage. It will record the wavelength in a very fast manner. Less than 1 second, you will record all the wavelength in a simultaneous manner. And then what they will do, the signal to noise ratio can be improved by calculating with the formula root of n. What is this root of n? N is the number of signals that are averaged. That means how many interferogram you are taking. If you are collecting hundreds and thousands of interferogram for all the source wavelength, everything will be getting averaged, right? So that is called root of n. Here n is the number of signals that are averaged. So this is the biggest advantage of FTIR spectrometer, which is also called as multiplex advantage or Felgate's advantage, right? The second important advantage is conus advantage. What is called conus advantage? FTIR is better in resolution than monochromator. Why we are telling this thing? When the previous dispersive spectrometer we are using monochromator, but in case of FTIR we are using, what we are using? We are using the, basically FTIR we are using interferometer. We are not using monochromator, and interferometer is always giving the better resolution. Why? Because the resolution can be given by the formula R is equal to 1 by delta centimeter inverse. What is this delta? Delta is the maximum retardation. Right? So R is equal to 1 by delta centimeter inverse if you are using. So the resolution will be better in case of interferometer rather than using dispersive IR spectrometer. Right? So that advantage is called conus advantage. And the last important advantage of FTIR spectrometer is your throughput advantage or Jacquinot's advantage. What is called throughput advantage? The term itself is indicating throughput. Completely you will be getting all the radiation. That means here, in case of dispersive IR spectrometer, we are using lot of optical elements, right? But in case of FTIR spectrometer, we are not using so many optical elements. We use only stationary mirror, mobile mirror, and one beam splitter. That's all. But in the previous case, dispersive, lot of mirror, lot of optical elements, slit, lot of things we are using. So here, there is a minimum utilization of optical elements. So therefore, whatever the radiation reaching to the detector will be a maximum input of radiation. That is why throughput radiation will be reached to the detector, which is also called as Jacquinot's advantage. So these are the three important advantages of FTIR spectrometer over the normal dispersive spectrometer. Most of the modern instruments are concerned with FTIR spectrometer only. I hope you understand it in a clear manner. Thank you very much, my dear students. Thank you very much.